another tutorial. My name is Tanmay Bakshi, and this time we're going to be going over how you can use CUDA C for general purpose GPU computing. Now this is actually a very interesting new series that I'm about to be working on. This is actually the first part of this new series, very first video in the series. In today's video, we'll be talking a bit about generally how GPUs work, how they compare to CPUs, and how CUDA itself works. Now, CUDA is actually a programming language that has C syntax that allows you to actually run general-purpose code on GPUs to use their enormous parallel compute power. Now, I will be talking about that in just a moment, but just before we begin, I'd like to tell you that if you've already watched my video where I actually show you benchmarks of highly parallel random number generation on CPUs using DigitalOcean servers, I'd recommend you actually go see that right now. There's actually going to be a link in the description if you haven't seen that already, because that is a good primer to this video to introduce you to the concept of multiprocessing and parallel computing. But today, I'm going to talk about how you can actually use NVIDIA GPUs and the CUDA programming language to implement simple CUDA applications, and later we'll get much more advanced and I'll show you how to integrate things like neural networks and more, and even other programming languages like Python and Swift with CUDA to create GPU-accelerated applications in all these different use cases. Alright, but today let's talk a little bit about the concept of this in the first place. Also, by the way, you need to know C for this to actually work and for you to actually understand what's going on in the first place. So if you don't already know C, do not worry, because in the next few weeks I will be releasing an entirely new series also about how C in general works, beginning to end sort of tutorial series on the C and C++, specifically programming languages, and how you can use them. Alright, but now let's get started with CUDA. First of all, GPU, CPU, what's the difference? Well, GPUs are meant for graphics processing, quite literally, as you could probably tell. Their name is a graphics processing unit. And so, the real difference between the GPU and the CPU is that since GPUs are meant to drive monitors with sometimes millions of pixels, of course it needs to be able to do tens of thousands to hundreds of thousands of things at once to quickly calculate all the values for all these sort of pixels that are on your monitor right now. And so what happens is, say that you've got an average CPU. And your CPU can do a lot of things, and it can do them very, very quickly. So say, of course, the average CPU, I don't know, maybe you've got, a Mac, or you've got an Intel i7. Usually these things are, quad core. So some average CPU that you might use might have 4 cores. However, Intel has a technology called hyper-threading, meaning that each core can have 2 threads on the chip at once. Now, theoretically, you can have many more cores than just 2 on a chip at once. However, they would have to keep coming into and out of the cache of the CPU, due to the fact that, of course, the CPU can only hold 2 in each core. And so what that means is that at maximum, at one time, 8 threads can exist on the CPU. So times 2, because each core can hold 2, and of course that turns out to be 8 threads on the chip at once. However, this is a little bit different for GPUs, because of course CPUs weren't necessarily meant to drive displays, say 5K displays, with hundreds of thousands to millions, to tens of millions of pixels. Forget multi-displays. However, GPUs were built to do this. So GPUs, however, are quite different. And not only in what I'm about to tell you, but they're also different in other ways, and I'll talk about that in a moment. Now, say that you've got a GPU, and say this is an NVIDIA Titan XP, or say, a Titan XP. A Titan XP, or let's take the example of a GTX 1070, that's a better one. So a GTX 1070, a GeForce GTX 1070 regular GPU by NVIDIA, has around 1,900 cores. That is a lot. But the best part is that each core can hold 12 threads. And so what this means, at once, 12 threads at once at least. And so what this means is that 1900 times 12, I mean, what is that? What is 1900 times 12? Whatever that is, but you're holding tens of thousands of things, of threads on the chip at once. And what that means is that, of course, you can do tens of thousands of things at once. And so there are a few limitations, though, because then you're probably wondering, and you might even have seen this Stack Overflow question, well then why don't we just replace all these CPUs with GPUs then? If these GPUs are so great, then why don't we just create these sort of GPU-CPU hybrids, or just use the GPU for the CPU? Well, there are a number of drawbacks from the GPU side. The first drawback is, of course, operating systems just can't run on them. There are some basic core features of a CPU that the GPU just doesn't have, and that's the reason that the GPU can do so many things. And in fact, yeah, so this would be around 22,800 threads on the chip at once. And so that's around, though, because it doesn't exactly have 1900 cores. It's actually a few more, plus or minus like 2 or 3. But still, you get a pretty good idea of how many tens of thousands of things you can actually run at once on a GPU. But the second limitation, however, is that GPUs can do a lot of things at once. But each thing that it does with less precision, and it does it slower than a CPU. Let me explain. The reason the GPU is able to fit so many cores into such a tight space is because it removes some of those, checks that the CPU makes to make sure that it's very, very precise in its calculations. For example, if you were to do a calculation on the GPU, you might be ever so slightly off with your floating point precision due to the fact that, of course, it doesn't have those checks that CPUs have, which is why it's able to do so many things at once. And also, second, each individual thing that it does slower than a CPU. Meaning that if you're only running one task on a GPU and one task on a CPU, you'd be way better off running it on a CPU because it can do that one task much faster than a GPU ever could. In fact, the GPUs, each core, can only really be used when you're using almost all of them at once, or at least a considerable amount of these threads, to make sure that you're using the GPU to its full potential. But that's just theoretically what they're capable of, and why we don't just replace all these CPUs with GPUs. In fact, a sort of good analogy here would be a CPU is a collection of, say, 4 extremely intelligent people who can do things very quickly, and they can do a wide variety of tasks. And in fact, they're so good at it to the point that each person can do 2 things at once, meaning, of course, hybrid setting. So you can do 8 things at once with this group of 4 people, and each thing is done very fast. However, when you load these 4 people with 1 billion tasks, or even just say 10 million, they will get stressed. However, imagine that you've got a group of 22,800 slightly less intelligent people. What's going to happen is you might have a few errors in the calculations that these people make. And these people might be slower at running the calculations themselves, but you're doing it in parallel. Everybody is doing a task, and that means that, of course, you're going to get to 10 million or even 1 billion much, much quicker than you ever would with the CPU. And this really explains the concept of how one task is faster on the CPU and slower on the GPU. Because one intelligent person doing a task is, of course, going to be faster than one slightly less intelligent person doing a task. And, of course, much more precise. And so that's a quick overview of the GPU versus CPU sort of comparison. But one thing I would like to tell you here is that GPUs, of course, are meant for graphics processing. The entire concept of running general-purpose code on a GPU is very, very new, or at least relatively very, very new. This has actually not been around for too long. It's a very new concept, which is why the community is still sort of building around this, although it has a very big sort of following in the deep learning and machine learning community, which is in fact why I got interested in this topic and why I'm creating this series today, or this series on my YouTube channel, because I want to show you how to incorporate deep learning technologies with GPUs in order to accelerate your deep learning workloads. And also one more thing I'd like to mention here Imagine, and I mean, if you're familiar with the concept of a neural network, you'll probably get this. Imagine you've got a very deep convolutional neural network with recurrent layers, etc., etc., or, just imagine a convolutional neural network, say Inception v3, okay, by Google. Now, this is a huge convolutional neural network. Layer after layer after layer, it is just absolutely huge. But it's also huge in terms of individual trainable weights. And so imagine this. You're doing a feed-forward pass through this neural network. So you're giving input into the neural network and expecting output from it. Now, say that you've got, of course, a few 100 million trainable parameters. Now, with these few 100 million trainable parameters, if you were to run that on a CPU, that would be very, very slow. However, if you were to run that on a GPU, that would be much, much faster to the point that deep learning becomes practical. In fact, that's the only reason why deep learning is used today and why it wasn't used in the past. Because now we have this computing power to actually run deep learning networks and have it practically run in terms of time. Because you don't want to have to wait for a month training your neural network model just to find out that it has, it overfitted to your data. You do not want that to happen. You want to do things very quickly, so you can, of course, deploy these models very, very quickly. But that's the first concept I wanted to explain. Second, let's talk a little bit about memory, shall we? Now, there are a lot of different terminology that I'm going to be using as I explain memory. So let's talk about terminology first. And even before we get to terminology, I have to explain how you can actually run code on a GPU in the first place. Now, theoretically, this should be very, very hard. However, thank you NVIDIA and the great people who are developing frameworks like OpenCL, because now, thanks to frameworks like OpenCL and CUDA, it's very, very, or at least much more easy to create these GPU-enabled applications. Let me explain. There are two sort of mainstream GPU acceleration options available in the market today. The first one is, of course, OpenCL. It's an open source platform that allows you to do GPU development, general purpose GPU computing, on a wide variety of different processors. Now, this can actually be your CPU. OpenCL runs on CPU as well, by the way. It also runs on the integrated graphics of your CPU. It also runs on AMD GPUs. It also runs on NVIDIA GPUs, although it's not very performance efficient, and I'll talk about why in just a moment. However, CUDA is basically a replacement to OpenCL that NVIDIA has developed. And so basically the difference between this is that it's proprietary. It's not open source. CUDA is not open source. It's developed and maintained by NVIDIA. And it is specifically optimized down to the core to work on NVIDIA processors and NVIDIA GPUs. And NVIDIA code is not compatible with AMD GPUs or any other GPU, only NVIDIA GPUs. However, CUDA is a lot simpler to program for, which is why I'm explaining that right now. I might have another series in the future about OpenCL and its development, and of course if you'd like a tutorial about that, please do let me know, and of course I will be glad to create those sorts of tutorials. But continuing for now, let's talk a little bit about terminology. Now that you know a little bit about CUDA, OpenCL, there are a few more like Metal, there's stuff like Vulkan, but I won't talk about that right now. For now, let's talk about the terminology that goes behind this development. Now, there is actually quite a bit of terminology that goes behind this. But there are two that you'll hear very, very often. The first one is host. The second one is device. Let me explain. Now, in essence, host and device are just fancier terms for CPU and GPU respectively. The host is the CPU because it's hosting the entire code. The device is the GPU. It's the device that all this code is running on. And that's why it's called host and device. There is a little bit more terminology though, one main one though being kernel. Now, at first, this might scare you that we're doing kernel development. No. All this is when you develop the actual function or the code that will be run on the GPU, it's called a kernel. Just like, for example, your operating system has a kernel, it's the same thing. It's just the code that's going to run on the GPU, nothing more about that. However, now let's talk a little bit about the steps you have to take towards GPU development to actually incorporate technologies like GPU acceleration into your applications. Now, of course, it has to begin with creating a CPU version of your parallel application. Now, what I'd recommend is actually creating a CPU version of your application before you try porting it over to CUDA. However, there are a few challenges with that, which I'll tell you in just a moment. But let's just imagine that I want to do something like, I don't know, matrix multiplication, which is something that, of course, deep neural networks require. Or even if I were to create a simple function that can take an array of, millions of values and run sigmoid on each value, that is a huge help to deep neural networks. And even if it's not sigmoid, it could be, rectified linear unit, hyperbolic tangent, softmax, whatever it might be. Basically just find a specific activation for all the values in this array. GPUs can do that very, very efficiently, but again, depending on how many of these elements you have, which I'll talk about in a moment as well. So imagine you wanted to build a CPU version of this application. The first step you would take is you would, of course, initialize your variables. By initialize, I mean you would declare or you would define and allocate memory for your variables. Because again, this is C, you're going to have to do this sort of manual memory management sometimes. But what you do is you would initialize your variables. I will fix that. But once you're done initializing your variables, there's still quite a bit left. However, again, you're probably used to CPU development, so this shouldn't be too hard. What you do is you would initialize your variables. You would fill the variables, or I'll just call them vars, with the actual values. Then once you're done filling it up with values, you would go ahead and then run sigmoid on the entire thing using something like a for loop. So you use a for loop to run sigmoid on all the values. Sigmoid the values. Now, once you've run sigmoid on all the values, you're almost done. All you need to do now is actually use those values in your application. And from there, you're ready to continue to the next layer or do whatever else you need to. However, with GPU development, there is quite a bit more, so get ready. Because with GPU development, it's not that easy, because with GPU development, you've got all this sort of memory copying, allocation, and transfer issues, which, let me talk about that. When you're doing GPU development, you've got two entirely separate memory spaces. You've got something called device memory, and you've got something called host memory. The host memory is your system memory. You're familiar with this. You use it every day when you're programming. This is the memory that all of your applications or code for the CPU run on. Then you've got your graphics RAM, or your the graphics DRAM. Now this is the actual RAM stored on your graphics card. In the case of a GTX 1070, you've got around 12 gigabytes of this DDR5X, I believe, memory. And so that, again, this is very fast memory, but you have to understand, though, that the GPU cannot necessarily quickly access the variables stored on CPU memory, and CPU memory cannot quickly access what's on the GPU memory, because again, you're linking this via PCI or PCIe, and so what happens is there's quite a bottleneck of that PCI from the GPU to the CPU. It's not as instant as RAM in those DIMM slots, and so you have to account for that sort of bottleneck, because imagine this. What you've got is you've got this thing called a device, and of course the device is your GPU. And inside of your device, you've got this thing called, DDR, or DRAM. You've got this DRAM in your GPU. And this is where you're storing, of course, all the variables that will be used in your kernel, and your kernel, of course, being the function that is actually called on the GPU. However, of course, you've also got your host, and you have to account for the host. And the host will actually do all the data generation. And so you have to have some sort of way to copy the variables from the host over to the device. Now, of course, you've also got memory inside the host, but there are two separate types of memory. There's pageable memory, and there's pinned memory. These are two separate types of memory. The pageable memory is actually, I guess you could say, it's not very performance efficient. It does this thing called paging, which I won't talk about right now. That'll get very, low level and technical. We'll have to get too deep into that maybe for another time, maybe in the C tutorials. However, what this means is that sometimes you could be using real RAM, sometimes you could be, you will be paging, you might be using swap RAM, you might be using, your hard disk as virtual RAM sort of thing, is what swap means. However, with pinned memory, there's actually a dedicated block of system memory dedicated towards these objects, or this specific object that you have. And so the pin memory is the only type of memory that can actually communicate with the DRAM on the device. And so somehow you have to use pin memory to send data up to the DRAM and down back from the DRAM. However, in order for this to happen, if you store your variables in pageable memory, which by default sees malloc function from the standard library, and generally whenever you allocate, you are allocating on pageable memory because, of course, the operating system doesn't want you to take up a lot of memory. The operating system will automatically give you this pageable memory. And so you've got two bottlenecks in this case. You've got the bottleneck of pageable to pinned, and then the bottleneck of pinned to DRAM. Now, the reason this becomes a problem is because CUDA has to do a lot more work to actually copy from pageable to pinned to DRAM, and from DRAM to pinned to pageable. It's not good. It's not efficient. You have to have a more efficient way of doing this memory transfer. And that's actually the hardest part of GPU computing. While each core might be ever so slightly slower than a GPU core, what happens is an even bigger bottleneck is actually introduced by the fact that you have to copy variables from CPU to GPU, you have to do processing on the GPU, and then copy them back to the CPU. It's not efficient, which is why you need to be doing a lot of tasks in parallel for GPU computing to even be worth the extra time that you're spending. However, there is a way you can make this quite a bit more efficient, from say 12 to 13 gigabytes per second. The way you do that is by, quite simply, erasing the pageable memory. You're just not going to use pageable memory. Only use pin memory, and it will create a performance difference, a positive performance difference. You will get performance gains. Now, the reason this is because CUDA is able to do a direct transfer without another bottleneck in the way, and so you're just doing direct DRAM to pin to DRAM transfers. And it should be, theoretically, much faster. And CUDA's memcopy, or memory copy function, becomes a lot faster this way. Now, if you've already used C in its standard library, you know about all these functions that I'm mentioning. I'm mentioning malloc, I'm mentioning memcopy, and of course these are great internal functions, but CUDA has their own version of all these functions. So, for example, when you need to copy a variable from, say, the host to the device, there's actually a function called CUDA memcopy, which will allow you to copy from the host to the device. However, theoretically, of course, if you were to just use a native C function to allocate your memory, it would, as I mentioned, allocate in pageable memory. However, there is actually a CUDA function called CUDA host alloc, or there's also CUDA malloc host, but I won't talk about that right now. And the CUDA host alloc will actually allow you to on the host, basically create or allocate this pin memory that can communicate directly with the GPU for much faster transfer speeds whenever you're using this variable to copy to and from the GPU. And so that's exactly how all the memory logic works. And I know it sounds a little confusing and you probably don't get it entirely right now. However, in the next part, when you actually see the code, which is coming out very soon, you will understand this in much greater detail. It's actually quite simple. It's not as complicated as I'm making it seem. It's really just one-liners. For example, when you need to allocate, you do CUDA host alloc. You pass it a pointer to your variable, and you tell it how big your variable will be, and there you go, you've done it. You've allocated the variable in pin memory on your host. That's it. When you need to copy, all you need to do is pass it a pointer to the destination variable in your device, a pointer to the source variable on your host. You pass it the size and where you want it to go, to the host or to the device. And that's really all there is to it. They're really just a lot of one-liners in terms of code. But getting back to the point from this memory sort of tangent here. Now this is how you would code in a batch sigmoid on the CPU. You'd initialize your variables, you'd fill the variables with values, you would use a for loop to run sigmoid on all the values, and then you would use your values in step number 4. So that's 4 steps. And of course there's no real complete bottleneck with sort of, memory copies from one piece of RAM to another. No, it's all, mostly clean, except for step number 3. Step number 3 becomes a huge bottleneck now, because now you've got, say, 10 million values, and you're individually running each one of those 10 million values and trying to run sigmoid on them. Not efficient at all. This is where the GPU comes in. If you were to implement the same application on a GPU, there would be a few differences. Let's take a look. The first 2 steps would remain the same. You would, first of all, initialize. I'm going to call them vars now. Initialize your vars, or variables. Then what you do, I'm just going to space it out so you can actually take a look at all these steps. Second, what you do is you'd actually fill up those variables with values. Okay. Now once your variables have values, it's time to get to GPU computing. Because what you have to do now is actually initialize. And remember, initialize, meaning define, declare, and of course allocate memory for your variables on the GPU. So you need to initialize variables on the GPU, on its DRAM. Once that's done, step number 4 is to actually copy the variables from host to device memory. So as you can see, basically what this will do is it will take the variables that actually have values in them that you created in step number 2, and it will copy them onto device memory into the variables you initialized on the GPU. This will allow the kernel to access these variables very, very quickly. After that, of course, you'll copy those variables onto the device from the host. After that, you have to run your kernel. So you run the kernel, which will do sigmoid operation on all of the array's elements. And then number 6 is you copy the result back onto the host from the device. So from device, of course, to host. And then once that's done, you are ready to use the values that you get back in your application. That's an entire 3 extra steps. Now, of course, this might not seem like a lot. However, think about this. There are a lot of bottlenecks, and if you're not doing enough things in parallel, you will run into performance issues, and you will find that the CPU is way faster than the GPU in some operations. For example, if I'm only running, say, 10 sigmoid values, then initializing the variables in the GPU, copying the variables from the host to the device, running the kernel itself, and then copying those variables back onto the host from the device will actually take more time than just step 3, or really the entire program itself. It's just not worth the extra time unless you're running highly parallel applications that require a highly parallel power of the GPU. Okay, now I do know that that sounded like a lot, and you probably are starting to understand a little bit of the concept and the sort of, the sort of beginner aspect, or the starting aspect of CUDA and how you should begin CUDA development. Now, of course, there will be a part 2 where I'll show you some actual code. I think this video is long enough for now. You might just want to, go ahead and see some more CUDA blogs, sort of digest all this content that I just gave you. But that's going to be all for this video. Thank you very much for joining me today. I really do hope you enjoyed today's video. If you did, please do make sure to leave a like down below and share the video with your family and friends if you think it could help them out too. Of course, though, if you have any more questions, suggestions, or feedback, please do leave it down in the comment section below. Email it to me at tadgymani@gmail.com or tweet it to me at tadgymani. Of course, if you really like my content and you want to see more of it, please do consider subscribing to my YouTube channel. And of course, turning on notifications if you think these videos help you out and you want to be notified whenever I release new content. Alright, so thank you very much for joining me today. That's going to be all for the video. Of course, do make sure to leave a like down below and subscribe if this content helps you out and you want to see more of it. Thank you very much. Goodbye.